so we're going to maybe learn how to make a 1 hour expression language. We'll see how that goes. So my name's Dan. I'm a contractor, basically. So if you need any contracts, I'm your man. So this talks about how to create an expression language, and what is an expression language, and what can an expression language do for you. But it will show you how to make an expression language and the three components that go into that, and the interesting things you can do with those. So I need to start my watch because I forgot. It's a useful thing to say there. So the talk's going to be 20 minutes or so of the presentation, and then 30 minutes actually making an expressive language from scratch. So what is an expression? So essentially, I mean, who's used like Symphony, right? And I expect all of you know what an expression is in terms of the Symphony expression language. No. Okay, good. That's the right answer. So an expression is basically, in this case, a string. So 1 plus 1. You can imagine if you've got a calculator, you type 1 plus 1, you press enter, you get 2. You type in an expression, you evaluate the expression, and you get a result. So an expression can be evaluated in any way you want. So 1 plus 1 wouldn't necessarily be 2. It depends how you evaluate it. It could be a concatenation. It could be 11. It could be anything you want, right? But what it is it's a binary operation with two operands. The first one is an integer, the second one's an integer, and the operator is a plus. So 1 evaluates to 1, true evaluates to true, foo plus bar evaluates to foo bar. It doesn't necessarily have to, right? That could be an addition. You could be adding the numerical value of foo and bar. So it really depends on how you choose to interpret that. Let's just say it's concatenation, so it's foo bar. You've got Boolean logic, so true or false evaluates to true, as you know. And 1 plus 2 equals 2 is an assertion that evaluates to false because it's not 2, it's 3. And things get interesting when you introduce variables, because if you introduce variables into an expression, then you can reuse that expression. You can create a rule and you can apply it against different subjects. Should have used my clicker really, shouldn't I? I wouldn't have to walk across the screen. So why do you want to make one? Well, maybe you need an expression language for some reason, right? Maybe you need to write a new tool, and you need to write rules, and you need to write a domain-specific language for it, an expression language. But there are other reasons you might want to make it. So by doing this, you'll learn how to make a parser, which is a very good way to parse incoming data and transform it into a form that's useful, a structured form, instead of just doing a regex, right? You get to create an AST. If you've ever used PHPSW, it's based on the PHP parser library, which basically gives you an AST of your code. And an AST is basically a graph of classes that represents the source code, right? And that's how PHPSW works. It analyzes the AST. So by creating your own expression language, you get to see how that works and why you have an AST and how you can use it and all the different ways you can use it. And it's the first step to writing your own programming language. So this is kind of the ultimate level of programming, right? When you actually spend like 2 years writing your own programming language. I haven't got there yet, but writing the expression language, it's very similar. It's a core part of any programming language, right? Use expressions every day. So concrete examples might be a discount rule engine in an e-commerce system. In that case, you don't actually use a parser, but you do create what is effectively an AST in the form of criteria objects, and then you evaluate them against products or the cart or whatever. Transpiling code. So if you generate an AST using a parser, you can use that abstract syntax tree, the AST. You can transform that into different things. So for example, I ported the VS Code language server protocol, which is in TypeScript, into PHP. That's pretty cool. It saves me a lot of work. You can write parsers for old font formats. If I was here last November, well, November before, I gave a talk about PHP TUI. I created a parser for that. It's very useful to be able to do that. And things like syntax highlighting and yeah, there's lots of things that are enabled by you knowing how to create an expression language, I guess. So that brings us on to what we're going to be creating. We're going to be creating something called ProCalc 2000. It's a calculator for the year 2000 and subsequent years. And it allows you to evaluate simple arithmetic without division. Actually, I got rid of the division because it confuses things. But essentially, it's a very simple expression language, but it gives you the building blocks that you can use to extend the expression language to any degree, really. So although it's only doing very simple sums, it would, it's a matter of minutes to add a division operator or add functions, variables, pipe operators, anything you can imagine. It's not that difficult once you've got the fundamentals. So how does it work? So there's basically 3 steps: tokenization, parsing, and evaluation. So tokenizing takes the string and it analyzes it, and it says which parts of the string are interesting and why they're interesting. So, for example, 1 plus 1, it will look at the first character, say that's a number. So that's a token, a number token of 1. And then it's going to see some white space, it's going to go ahead. And then it's going to see the plus operator. Well, that's an interesting token, that's a plus token, and so on. And then you have the tokens, and then you pass the tokens to the parser. And it's the parser's job to make sense of the tokens and to transform that stream of tokens into something with structure that can be used, as I've mentioned before. And then finally, you've got the AST, this tree of nodes, and you can evaluate that, again, in any way you choose, really. Today, we're going to evaluate it, and it's going to do the arithmetic. The evaluator is going to perform the arithmetic on this AST. So we've got the 3 classes that we'll create today. So tokenizer, parser, evaluator. Just diving a little bit deeper into the tokenizer. So basically, it's just going to scan from left to right. So that's the expression. It's going to start at offset 0. It's going to say, okay, that's a 1. It's going to go to offset 1. That's a 0. These are 2 numbers. It's going to look ahead and say, oh, that's a space. Okay, so I'm going to take those 2 numbers and say that's a token of type number with the value of 10. And then it's going to skip the space and go to plus, so that's the plus token, as I already said. So the final result of this, tokenizing this expression, would be a list of 5 tokens which get fed into the parser. And of course, I've skipped ahead and already explained most of this. But our parser will only have 2 nodes. So it's going to have an integer and a binary operation. So a node to represent a number or an integer number, and a binary operation to represent a number and an operator plus minus multiplication and another number. In a real AST, you might have hundreds of these node types. If you look at the PHP one, there's a very long list of these node types, but we start simple and we've only got 2. The AST will look like this. So if we've got 1 plus 1 divided by 5, that translates to essentially to a single node, and that single node is a binary operation, and that is the AST. And then you've got the left operand, which is an integer, this one, and then you've got the entire right-hand side, which is also a binary operation, 1 divided by 5, and then the left is 1, the right is 5. We're missing something very important, or at least not necessarily important, but something which you might find a bit weird, and we're not taking into account operator precedence, which means that if you have a multiplication and an addition, or an addition and a multiplication, you should always do multiplication first. At least that's what we expect, how we expect things to work. We're not going to do that because it's slightly more complicated, although you can do it like in 10 minutes or something. But it is a bit mind-blowing and complicated and recursive, so I'm not going to do that. So the binary operation is that simple. Like that's the node. That's a node. just 3 properties. The integer node's even more simple, just the value. And then this is the AST essentially. So this is the result of the parser, i.e. a binary operation, 1, and yeah, you see that's the AST. Then we have the evaluator. The evaluator's really powerful, actually, and also incredibly simple. So essentially it takes a node and it returns something. It could return a string. It could pretty print an AST. It could do anything you like. This pattern is very flexible. In this case, it's going to evaluate the AST to an integer. So the first thing it says is we pass in a node, and then we say, is this node an integer node? And if it does, we return the value. We're done. It returns the integer. If we pass in integer 1, it says, okay, it's an integer, I'm going to return 1. Things get interesting when we get to the binary operation, because then we say, okay, this is binary operation. Let's evaluate whatever is the left-hand node. In this case, it's an integer. So then we evaluate, we recurse, and we go back here. This is the integer node. We get 1. We come back. We've got the left value as 1. We've got the right-hand value, which is another binary operation. So we go in here. It's binary operation. It's recursive. And eventually it evaluates also to an integer here. And then we simply match on the operator. So this would be plus, minus, divide, whatever, and perform the operation. And that's it. That's the calculator, right? It's pretty easy. You can fit it on a slide. Okay, so obviously this is the first time I've done this live. All the demo ones I did, all the warm-up ones I did took 22 minutes. This has only taken 11 minutes. This is very good, because otherwise this would take an hour. So hopefully this will take less than an hour now. Okay, and this is the tricky bit. Hopefully this is going to be fine. So we're going to code the expression language from scratch. This is the project. Composer, there's essentially nothing. I've got PHP unit and PHP stand there, but I'm not requiring any dependencies apart from PHP unit. I've included a REPL. So this is a really hideous, horrible script that just provides kind of a command line interface to our expression language. The first error is that the tokenizer doesn't exist, which points us to the first thing that we need to implement. Okay, and I've also taken the liberty of creating some skeleton tests for each of the three classes. So let's go. Okay, so the first task is to create the tokenizer. So if we're doing test-driven development, this is the evaluator, sorry, this is the tokenizer. Is everybody kind of familiar with PHP unit and data providers, more or less? So we're going to pass in the expression here, and then we're going to pass in the expected tokens. So the expression's going to be 1 to start with, and the expectation is that we have a token. So now I'm writing classes that don't exist. We're going to have an enum token type. The token type is going to be integer, and this token is going to have a value. There's lots of ways to implement tokens. Sometimes you can just store the offsets within the string when a token starts and finishes. We're just going to store the literal value in the token. So that's our expectation, and then we're just going to create the tokenizer that doesn't exist, and we're going to tokenize the expression, and the result of that is going to be some tokens, and the tokens should equal the expected tokens. So then we can run the test. We have to run the right test, which is the tokenizer, and it fails. And the first thing it's failing with is that the token doesn't exist. as you'd expect, right? Because we haven't created it. So the src directory is empty. So we're going to start by creating the token. Like I said, this is going to have a token type, which we'll see in a second, and an optional value. So not all the tokens will have a value, like integer has a value of 1, 2, a string might have a value or something, but like an operator, like a plus, it can only be one thing. So the value is going to be optional. Let's create the token type. So it's an enum, and it's going to have, I think, so every time I've demoed, every time I've practiced doing this, it changes. So every time I like to think it's a little bit better, but it's also quite risky. So I only did this on the train. I had a different strategy before. So we're going to have plus, minus, and multiplication. So these are let's call it multiply. So these are the 4 token types in our expression language. So we can have plus, minus, multiply, and we can have numbers, and that's it. Okay, so that's our token. We also need a tokenizer, of course. So let's create that. And feel free to stop me at any point and ask questions. So the tokenizer is just going to have, I think, again, I changed this in the train. It's going to have tokenize, yeah. Tokenize, tokens, no, that's not right. Tokenize string. So tokenize the expression, return tokens. There we go. Tokens is a collection object, so we'll need to create that. So I'm a big fan of collection objects, and all my collection objects implement iterator aggregate. So this is, you could return an array of tokens here, but returning a collection object, it gives you a lot more flexibility. In this case, it allows us to keep state in this returned object, which is useful, as we'll see later. So tokens, like I say, the tokens will accept an array of tokens. Sorry, the token, yeah, I did say that, that's fine. So return new array iterator, this tokens. Okay, so that's our tokens, that's our tokenizer. And we can go back to the tokenizer test and import all the classes. So yeah, we want the token and everything else. So let's see if it works. Okay, so this is a more positive error, right? So tokenizer return value must be of type token, nothing is returned. So now we're down to the meat of it, I guess. So as we saw in the slide, what we want to do is go from the left of the expression to the right. So if we just look at what we're working with here, so we're working with 1. That's what we've got. So what we need to do is get the first character. So we're going to have an offset here, and we're going to say while the offset exists within the expression, get the first character in the expression, increment the offset. So this is going to return the 0th, like the first character in the string, character, and then it's going to increment the offset. So the next time we call this, it will already be on the next character. So that's why plus plus is there and not there. Otherwise, yeah, it would return the next character. So yeah, let's see if that works. So that should return 1 as well. Yeah, that's 1. And then we can just say, okay, so what sort of character have we got under the cursor, under this pointer right now? So if we say it's numeric, this isn't a great way to do this, or is it? It's not a bad way to do it, I think. I think it's fine. So if it's numeric, so we need to return like a collection of tokens. So we probably want to start building a collection. So we can say tokens, and then we can say new token, and we can say token type. And it's the integer. And the value is going to be char. We run that, it doesn't return anything, so we need to return the tokens collection object. And, and then we've got a problem in our test. So let's have a look there. And the problem is we're passing in an array, and we're comparing it with our collection. So that's our token collection. And we need to compare it with the collection. And we need to import the collection. There we go. Let's get rid of that one. Good, so one passing test, first passing test of the day. So what happens when we pass in 12? So if we pass in 12, it shouldn't return 2 tokens, it should return 1 token with a value of 12. It returns 2 tokens because our tokenizer is really stupid. So what we need to do is when we see the numeric character, we need to look ahead, or actually look at where the pointer is right now and say, is that a number? Also, is this also a number? And if it is, we need to kind of consume that number and add it to the string that we're building up representing that number. So, and to do this, we can do another while loop. And we're going to say, while is numeric, sorry. While is numeric expression offset. We're also going to say if the offset doesn't exist, just return null, and null's not numeric, so that's fine. And we're going to cheat horribly and just concatenate the character. So if we're at offset 1, then in this case, if the expression is 1, 2, 12, if we're at offset 1, the character is going to be 2, char is 1 there, and then we append 2 to char so that we've got 12. And if it was 1, 2, 3, it would, until basically the character is not a number. So we're just going to consume the number, and that should result in an infinite loop. So we also need to increment the offset again. Otherwise it just goes on forever. Yeah, maybe undo that. So good. So now we can pass numbers. We can prove it if we run our REPL. So 1. Okay. And we come to another problem. Can you guess what the problem is here? Yeah, so there's no assignments in this structure, right? So we need to promote so that's basically as if we created those properties and we assign those properties, which I forgot to do. So now, it's funny, the test didn't pick that up because token and token are exactly the same if you don't assign anything in them. 1 plus 2. Interestingly, it returns 1 and 2, and it skips the plus. 2, 12, 1, 2, 3, 4. So we can see now that we've moved on to the next stage. We've got, we're passing the token, the number. So let's just add another test case here. So now we've got 12. Let's do 1 plus 1. So that should be 3 tokens. Oops. So that's 1. So I said that the value is optional in this case. So plus doesn't need a value, and then 1. Let's run the test. And it doesn't work. What's happened here? So we get, it's actually hard to tell, isn't it? Let's have a look at the tokenizer. So first of all, once we get the token here, we can continue. This isn't necessarily a lesson on how to write really neat code, by the way. You could refactor this to be a lot more understandable and scalable, but I just want to crack through it without refactoring things too much. So here, now we've got a space. Actually, just start with plus. We'll just get the plus token in there. Yeah. So now we've got a plus, and we need to change that plus into a token. So here we can use a match expression. So we're going to match on the char, and if it's a plus, we'll return a token and token type plus. And if it's a minus, and if it's a, what was the other one? Multiplication. So minus, multiply. And then it's always good to throw useful errors because that makes the people that are using your expression language very happy. So invalid operator, or yeah, why not? And we're going to quote the char that it is, and yeah, and that's not how it works. So default, yep, cool. Okay, so another green test. Finally, we're just going to do the 1 + 1, and we see our exception coming into the fore. So invalid operator space. So spaces don't mean anything in our expression language. You can have as many. They're like comments. We just skip past them. They don't count. They're just for the humans that read them, which isn't necessarily always the case, by the way. You might want to preserve spaces in your parser. In our case, we don't want to preserve the spaces. We don't want to preserve the white space. So we just want to skip past it because it's meaningless after this point. So we need to refactor the tokenizer to skip past the white space. So what we're going to do is also match on char. So if it's a white space, we're not going to bother with tabs and things like that. Well, we can't return a token. We could return a token, but not with this design. So we're just going to return null. And if the token is null, we're just going to ignore. We're not going to add it to the list of tokens. So I'm just going to continue. Otherwise, yeah, whatever the token is, we're just going to add it. And there we go. Oh, delete too much. Okay, so that should work. And we've got a failing test. Yeah, so it's 1, which is an integer, 1 + 1, and that should pass. So now we can run our parser, and we get the token list. So the interesting thing about this token list is that this isn't a valid expression, or at least if we say that we're just doing an arithmetic calculator, that wouldn't be a valid expression. But the tokenizer doesn't care if it's valid or not. It just tokenizes stuff. So the thing that does care about this is the parser. So now we're done with the tokenizer, and we're going to move on to the parser. So again, we have the parser test. I say the parser is going to accept tokens, so we can reuse our tokenizer. So we can say new tokenizer, and then we can get the tokens for the expression. So this is the parser test. That wasn't clear. So we're going to tokenize the expression. And then we can pretend that this class exists, and we're going to say the node, or the AST, equals, and we're going to instantiate the parser, which doesn't exist yet, and we're going to call parse, and we're going to pass the tokens. And then we're going to say, assert, is this equals, the expected node, so the thing we're passing in is going to be equal to the AST. And then the first case is going to be 1. So that's going to be tokenized as it's the number token, and our parser is going to interpret that number token as an integer node. So again, another class that doesn't exist. Integer node 1. Oops, come on. Cool. Of course, now the test is going to pass. Yes, we've got to write the right test, pass the test. It's failing because none of the classes exist yet. So let's create some classes. So like I said, we've got 2 node types, so we're just going to proactively create those now. So we've got integer node.php. Very simple, just represents an integer. So I'm going to use public properties. These can also be final and read only, right? They don't, yeah, they're pretty dumb. They're just data. Then we're going to have the binary operation node, binary op node. And that's going to have null, no. That's going to have a left node, an operator. So this is going to be plus minus multiplication. You probably want to use, like in your one, if you ever make one, binary op kind or binary op type, use an enum. I'm not going to bother because I'm lazy. So, yeah. So binary operation, just left, operator right. These also implement, or should implement at least, either extend an abstract class called node. It doesn't have to be called node, you can call it whatever you want, expression, criteria, whatever. We're going to use node, but they should implement something at least so that you can categorize them and say, yeah, I accept a node, I accept a node. Even though they, at least in our implementation, they don't have any methods on them. They don't have any behavior, but it's just to be able to mark them. It's a marker interface in this case. Okay. So we've got the nodes. Let's run that. And we need to, well, let's create the parser as well. Let's create the parser class, because then we've got everything we need. Doesn't matter if it's final. So yeah, it's going to have pass. It's going to accept the tokens. And it's going to return a node. And the node is essentially the root node of the AST. Okay, so let's go back to our parser test. Import the classes. I get to choose which. There's so many parsers. I think, yeah, in your project you probably have 100 classes called parser. Good. Okay, so now the test is failing because. Why is it failing actually? Argument 2, expected node must be of type 1-hour expression. Okay, so I think I forgot to implement the, yeah, implements node. Okay, so now we're at the good failure, which is where we need to start implementing our behavior. Right, so writing tests is always like this. You battle through the crap, and then eventually you get to the bit where you actually deliver value, right? Where you're actually working on the thing you want to work on. So let's go to the parser. So we've got a stream of tokens. Let's have a look. So our stream of tokens at the moment is just one token. It's an integer. It's got the value 1. So we can be very stupid here and say, so we're going to say node equals, we're going to take the first node from the list, whatever that node is. And by the way, if you've worked with parsers before, our tokenizer is also known as a scanner. It's also known as a lexer. You get lots of different terminology for the same things. And then your tokens, you'll often get parsers that call this operation chomp, eat, consume, take. There's no limit. People just go wild with this, right? We're just going to use take. And what this is going to do, it's going to take a token, and in our case, it's going to move the pointer to the next token. You could also just have a stream that you consume. You could use a generator here and just pop tokens off and keep, and you could sort of tokenize and parse at the same time. We're not going to do that. So we're also going to return null. So we return a nullable token. So if we're at the end of the token stream, we're just going to return null. So return this tokens, this offset doesn't exist yet. And again, we're going to increment the offset. So that expression is going to return, thanks Vim. So that's going to return the nth token here. And that expression offset plus plus is going to return the current offset, then increment the offset. So let's create our offset here. So it's an int, it's an offset, it's 0. Okay, so that's going to take whatever the current token is and move the pointer ahead. So, oh, that's not node. So token equals token stake. So let's dd the token and see what happens. Good. So we've returned our first token. And yeah, I think we can just say if the token type is token type integer, then return a new integer node. And then because we've stored the value as a string in the token, we can just cast that string to an integer. So, yeah, so passing test. Fantastic. We can also go to our REPL and we can say 1. And you can see we've got our token, we've got our AST, and our AST is the integer 1. So let's make it more interesting. So we're going to introduce the binary operator, not in this test, parser test. So we're going to do 1 plus, I don't know, 2. Now this is going to be the binary operation. We've got the left, we've got the operator, and then we've got the right. So that's what should happen. So I'm going to run the test again, and yeah, of course it fails, although not for the reason I thought it would fail. So I've disabled PHP stan. I probably should have enabled it, because then it would have told me that. Yeah, didn't import the node. So again, yeah, now we get to the bit we're interested in. So of course our parser, it just returns the integers and doesn't do anything else now. So what we need to do is take another token and say, is this, are we at the end of the stream? Is this next token, is this an operator? And if it is, we need to return the binary operation. So what I'm going to do is I'm going to say node equals null. So we're going to try and resolve an operand here. If null, oh sorry, let me assign, so if we have an integer, so at the moment our expression language only has integers, doesn't have strings, doesn't have functions, doesn't have anything like that. But this is the bit where we pass that operand, and our only operand at the moment is integer. So if the node is null, then we did not pass our operand. Yeah, at points like this, your error message should probably include something like the point in the expression where the error happened, in which case you'd need to store the offsets of where the tokens are and things like that. We're not that advanced at the moment, so we're just going to say, do not know what to do, thanks. And yeah, for that token type, and it's an enum, so we can use name. Good. So then we can proceed. So let's assume that we've passed our integer node. We've got the integer. This is the left. Then we need another one. So let's see what our next token is. It's null. Okay, why is it null? So we've got the tokens. We take it. Ah, I know why. Yeah, so the token is null, And if the token's null, that means we're at the end of the expression, because the first test is just 1. So it gets the 1 here, says that the left node, or the node, is an integer node. We have the node. And then we take another token, but the token's null. And that means that there's no more tokens. And if there's no more tokens, we are going to return the node. That's it. So job done. Our second test was 1 plus 2. So now we get to here. So now we do have another token, and the token is a plus. And in our expression language, we only have 2 things. So it can only be a binary operation now. So let's return a new binary operation node. We already know what the left-hand operand is. We need to, so I could make this better. So basically, we're going to pass in a string representation of the operation to the binary operation node. So we need to match on the token type. So token type, if it's a plus, then the operator is going to be plus. If it's minus, it's going to be minus. And if it's multiplication, it's going to be multiplication. So just minus, multiply, otherwise throw new runtime exception. I don't know why I use runtime exception for everything, but that's just me. Unknown operator. And then we can say what operator it is. And that should be, that's not how it works, it should be default. So the match expression allows you to specify a default like that. And it's an expression, unlike a switch statement. So the interesting bit, and the really powerful bit, is where we get the right-hand side, and that is literally just calling parse again with the token. So the right-hand side is the whole rest of the expression. And this is also where you implement your operator precedence thing, because then you've got to do the multiplication first and fiddle things around with a lot of recursion. But like I say, we're going to skip that. So the right-hand side is always the rest of the expression. And let's see if it works. It does. So let's try it in our REPL. Awesome. So we got our AST. Now our AST is a bit more interesting. So we can now do 1 plus 2 plus 3 plus 4 times 100 minus 1,000. And then we get, that's our AST. So what can we do with our AST? We can put it into our evaluator. Our evaluator's a tree walker, essentially. This is a tree structure, right? And an evaluator, a tree walker, will walk this structure and do various things for various different node types. So, evaluator test. So we have 1 should return an integer 1. So again, I'm going to cheat again. Maybe so. Again, we need the tokenizer. We need the parser. So I've just copied that. So we've got the AST. So the it's going to run the test. It's the evaluator test. Yeah. So great. So we get 1. We pass the 1 and we get the AST. Now we need to feed it into the evaluator. So let's create the evaluator. And let's evaluate the AST. And so the result is that. And then we're just going to assert same expected value result. Okay, so I could run the test now and it would fail because the class does not exist. So let's create the class evaluator.php. Let's import the class into the test. Let's generate the evaluate method with magic. So evaluate is going to take the node, we'll rename that to node, and it's going to return an integer. In your one, it could return mixed, it could return a string, it could return booleans or whatever. Or you could return another AST even. This class can transform an AST into anything. In this case, it's going to transform it into a result. So The first case is just, is it an integer node? Because it is. If it is, that's a constant value, and we just have to return it. So our test should pass. So let's do 1 plus 2 plus 3, which is 5, 6. Yeah, thank you. 6. Okay, so now, again, like throwing useful exception messages is really useful, surprisingly. So we can say, do not know how to evaluate node and the node type. So this is, yeah, this is an error message I'll run into continuously when I'm developing an expression language. So yeah, do not know how to evaluate the binary operation node. So let's sort that out. So instance of binary operation node. So yeah, this is where we're going to do the arithmetic. So we're going to do another match on the, why didn't that work? Why have I got no auto completion? Okay, because it's fucked up. Yeah, there we go. So yeah, if the operator is plus, then, well, we need to kind of use integers, right? But at the moment, we've only got nodes. So we've got a node there, and we've got a node on the right. And what can we do with nodes? Well, we can evaluate them, right? So we need a left value for plus, a right value for plus. So let's evaluate the left and right sides. So left value. So then we can recurse and say evaluate node, the left one, right? So this would be integer 1. And then we're going to evaluate the right one, which is a binary operation, but it could be anything. But at the end of it, actually, let's change the return type to int. So it's always going to be an int, or it's going to be an exception. So we know this is an int, this is an int, and we can say left plus right. And there we go. We can support the other operators very easily. So minus is minus, multiplication is multiplication. And then again, we're going to throw an exception. New throw exception? No, that's not right. Let's go with an exception this time, not a runtime exception. Yeah, again, could probably factor this out if we had enums. If we used an enum, but we didn't, maybe for next time. Cool, so that's the evaluator. That's it. And the test pass, and then we can load up our REPL and say 10 plus 19 plus 1. And the evaluator returns the result. 20 plus 10 plus, I don't know, something stupid. So that's it. That's our super duper over-engineered calculator. Like I say, it's very easy to extend this and take it further. But these three classes, these are the things you can iterate on. So you can almost develop an expression language with any grammar, with any complexity, using these three classes. If you're interested in learning more, I highly recommend this book. It's kind of like a tome. It's very big, and it takes you through creating a programming language, including the expression evaluation bit, and it takes you through creating a parser, a program language. It takes you through like allocating memory and everything. And the first part is in Java, so you get to write a programming language in Java, which is very easy to do in PHP. I mean, it's the same language basically, right? There's hardly any difference. And then the second part is about C. So it takes you through writing the same programming language, first in Java, and then secondly in C. So you actually get to write like a real programming language. And if you're interested in implementing operator precedence parsing, I also recommend by the same author, he's got a blog post about PRAP parsing. So just Google Pratt parsing, Robert Nystrom, and yeah, he basically tells you how to create a parser with operator precedence and stuff like that. So that's it. Are there any questions?
Is the tree that you're always building always going to be linear? I mean, I know there's a possibility of putting something like brackets in there, which would be good for the
precedence. Yeah.
Yes.
Yeah.
But with those brackets, as it's written, go in a linear format.
I mean, there's no recursion in the tree, right? So it's you parse it and it's. When you mean linear, do you mean like linear time or?
Well, there's just one thing following enough. There's no if you had a difference in operator precedence, the tree would have something nested in it where brackets are.
No. So you can have brackets, and they'd be part of the AST. I think. No, they wouldn't be part of the AST. The brackets would be removed, but the AST would be rearranged to respect the operator precedence. So whilst you're building the AST, whilst you're building this tree, you basically change where the nodes are. The order would kind of change, if that makes sense.
Brackets had to change that. It wouldn't know that automatically. No, of course, it wouldn't know that automatically. Maybe I've asked my question there. It just seems wasteful otherwise having this linear structure in a tree. Maybe but perhaps it makes more sense, more complex sense that it could do.
I mean, it's you're building the structure, but for addition, you can make a much simpler calculator, right? But this is about making essentially half of a programming language, the expression part, of a programming language. So it's yeah, I think so. Yeah, go on.
Just a follow-up question, just trying to think it through out loud, but I think what you possibly could do, because just run it through, I think when you build up the parser, presumably when you get onto the Pratt parsing outpost, maybe what you could do is start by scanning for an operator. If you start off with divide, let's say you haven't got a divide, then you scan for multiply, got one. If that's at position 4, then you put in the binary operator, and on the left-hand side, you call parse recursively with 0 to 3, and on the right-hand side, you call parse recursively, put 5 to the end. So basically, start rather than you basically build up an evenly balanced tree by looking for the operator first, I think, and then you could add brackets in, having the highest precedence.
Yeah, I've only done it with the Pratt parsing when that does it with effectively by specifying a precedence and then recursing based on if this operator has a higher precedence than that operator, and then sort of building up.
So you say at the point where it builds up the tree, builds up the parse tree, does it?
Yeah.
You end up with a balance to the parse tree based on precedence.
Probably. Yeah.
But yeah, I was just going around in my head. I think that's the main piece. I think if you're always looking for a token first, a number first, you'll always get that lopsided tree, won't you? But if you look for the operator first, then you add the left and right.
Yeah. I think I know what you mean. Yeah. Yeah. All right. Well, that's yeah. Go on.
When you use this in sort of like in another scenario, so something that's not number passing, something in production where it's not calculated, essentially as simple as that.
So like a discount rule engine on an e-commerce system. Although, sometimes you have discount rule engines where you write expressions, but that's not really that user-friendly. Normally you build it up with a GUI. But the interesting thing is that GUI, that's actually represented with an AST in your code. So that GUI, you might have a number and a percent operator, or a comparator. So this, the price on this product has to be greater than that. In your code, that's represented in what is essentially an AST, right? A tree of nodes. and then you're just passing it off to the evaluator. Yeah, and what was the other example? I was blowing my mind now. I've forgotten. But does that answer the question? Yeah.
Do you know the search thing in GitHub where
Yeah.
you can do like status code over the repos?
Yeah, exactly.
You can do dates, range, and author.
Yeah.
Would something like this be overkill for implementing that?
No, I mean, that's pretty much what they do. I mean, yeah, even down to like the tokens, you know, you're basically building up an AST there. And even the syntax highlighting, you know, that's based on tokens. It can also be based on the AST. But yeah, syntax highlights is typically based on tokens. So any one of these three things, the tokenizer, the parser, and the evaluator, they can all be independently useful. Yeah. Yep.
I just wanted to add an example of where I've used this before. I think it's interesting, which was so I made a templating engine. So the idea being that you would write HTML and it would have keywords and stuff embedded in it.
Yep.
So we could let front-end guys write HTML and then stick some keywords in it, and then when that's processed by PHP, it would evaluate the stuff inside it, and then build you an actual sort of processed PHP stuff.
Okay.
I don't think that's definitely not the only way you could do that, but it's what we do.
So you made a HTML parser.
No, it was. Yeah. it was like we made like a very simple language within an HTML page.
Okay. Yeah.
It was like a very simple language.
A DSL. Yeah.
That's what we do.
Cool. Thanks.
Thanks very much, Dan. That was incredible.